Welcome to the second module of the Soot-free and zero-emission urban bus fleet technology transition curriculum, where we will be breaking down the technology pathways for you. In today's Module 2A, we are presenting the internal combustion engine bus technologies that meet our definition of soot-free and zero-emission, and we'll go over performance, emissions, and cost.
Before we begin, here are some key terms and acronyms that we'll come across. Air-to-fuel ratio is the mass ratio of air to a solid, liquid, or gaseous fuel present in the combustion process. Air-to-fuel ratio determines whether a mixture is combustible, how much energy is being released, and how many unwanted pollutants are being produced in the reaction. Biodiesel is a type of fuel that can be manufactured from vegetable oils, animal fats, or recycled restaurant grease for use in diesel vehicles or any equipment that operates on diesel fuel. Biomethane is a near-pure source of methane produced either by upgrading biogas, which is the product of anaerobic digestion of organic matter in an oxygen-free environment from different feedstocks, or through the gasification of solid biomass followed by methanation. Brake thermal efficiency measures how efficiently an internal combustion engine converts the heat from fuel to mechanical energy used to power the vehicle or equipment. For different sources of energy and different fuels, carbon intensity is a measure of the amount of CO2 emitted per unit of energy output or heat content. Diesel particulate filter is a type of emission aftertreatment technology for diesel engines. It captures the solid fraction of particulate matter, including black carbon, from the vehicle exhaust. It also effectively reduces CO and hydrocarbon emissions. Diesel oxidation catalyst is also a diesel engine emission aftertreatment technology that uses precious metals to remove hydrocarbons, carbon monoxide, and the soluble organic fraction of diesel particulate matter. Lean burn and stoichiometric combustion refers to two kinds of air-fuel mixtures and their combustion processes. Stoichiometry means the ideal theoretical air-to-fuel ratio for complete combustion of a fuel. On the other hand, lean burn happens when the air-fuel mixture is higher than the stoichiometric ratio, which is to say when there is an excess of air. Selective reduction catalyst is a diesel aftertreatment technology to convert NOx to water and nitrogen over a catalytic surface. A three-way catalyst is an aftertreatment system in gasoline and natural gas engines. It oxidizes hydrocarbons and carbon monoxide and reduces nitrogen oxides present in the exhaust gas. We came across ultra-low sulfur diesel in Module 1, and it refers to diesel with sulfur content lower than 15 parts per million. Diesel with this amount of sulfur is required for advanced emission treatment technologies like DPFs and DOCs to properly function. Well-to-wheel is an accounting method that encapsulates the life cycle emissions of greenhouse gases. It quantifies emissions of activities and processes required to deliver the fuel or energy to a vehicle, from its extraction and production, distribution, and end use, as opposed to just the tailpipe emissions.
Soot-free and zero-emission is a technology-neutral term that does not prescribe any particular type of engine technology. It covers a wide range of engine options that include both internal combustion engines and zero-emission electric drive engines. In this Module 2A, we will focus on the internal combustion engine technologies that meet this definition. For our purposes, the most common soot-free internal combustion engine buses are Euro 6 or Euro 6 equivalent diesel and CNG buses, as well as hybrid buses. We will cover zero-emission electric drive technologies in the next module, and at the end of both modules, we should have a good sense of the relative performance of each type of bus technology. Here are today's learning objectives. To understand the definition of soot-free zero-emission technologies and engine options that meet this definition. For internal combustion engine technologies, understand the combustion processes and emissions, the fuel consumption and performance as a baseline, emission control technologies, and recent bus deployments. For alternative diesel and CNG sources, understand how fuels and feedstock production may increase the GHG emissions of the fuel, and learn about the key components of a hybrid-powered bus and their performance and emissions. Diesel and CNG engines are the two most common types of internal combustion engines found on urban transit buses. They represent two combustion processes, lean burn and stoichiometric. Stoichiometry means the ideal theoretical air-to-fuel ratio for complete combustion of a fuel. When the air-to-fuel ratio is higher than that stoichiometric ratio, the air-fuel mixture is called lean. Due to the nature of the combustion process of compression-ignition diesel engines, their air-to-fuel mixture is lean, meaning that the diesel fuel burns with an excess of air. The air-to-fuel ratio may be as lean as 65:1. On the other hand, most CNG engines in HDV and bus applications are stoichiometric. These stoichiometric auto-cycle CNG engines behave much like a gasoline engine with a spark plug. Stoichiometric natural gas engines have a relatively low brake thermal efficiency and are also worse off in terms of fuel consumption and greenhouse gas emissions. The advantage is that they produce lower levels of engine-out particulate matter, hydrocarbon, and carbon monoxide pollutants and require a relatively straightforward emission control system based on a three-way catalyst. Compression ignition diesel engines do have higher brake thermal efficiency, and the advantage of that is lower fuel consumption and GHG emissions. Conversely, compression ignition engines produce higher emissions of pollutants like PM, HC, and CO due to air and fuel mixing challenges and incomplete combustion. A rather complex aftertreatment system is needed to control for these emissions so engines meets the most stringent emission standards. This is part of the reason why so many older diesel engines are considered high polluting. Thankfully, with adequate in-engine and after-treatment emission control technologies, both types of internal combustion engines are capable to meet Euro 6 or EPA 2010 emission standards and can be considered soot-free. Let's start with diesel urban transit buses. As mentioned earlier, diesel engines are compression ignition engines as opposed to gasoline engines, which are spark ignition. Air is compressed to a sufficiently high temperature to ignite diesel fuel and injected into the cylinder, where combustion and expansion actuate a piston to generate energy. Diesel engines have the advantage of being efficient and delivering great fuel economy, which is why they are popular for commercial and heavy-duty vehicles. However, engine-out emissions of particulate matter and NOx are higher for diesel engines than gasoline and CNG heavy-duty vehicles. This has promoted the development of modern emission treatment control technologies to reduce air pollution from diesel engines, as we mentioned in Module 1. Currently, Euro 6 diesel engines make use of the best available emission control technologies and represent a huge step forward in terms of air pollution reduction. With the introduction of diesel particulate filters, Euro 6 diesel and equivalent engines achieve a 90% reduction in PM and NOx emissions and a reduction in particulate number by 99.5%. DPFs are a game changer for removing PM from diesel exhaust. Other components of the modern diesel aftertreatment system are diesel oxidation catalyst, selective reduction catalyst, and a urea injector to make SCR function properly. DPF, DOC, and SCR are part of the same emission control system that achieves the best reduction results of exhaust pollutants. These systems require ultra-low sulfur diesel, 10 to 15 ppm, to function properly. A very visual comparison of DPFs using two kinds of diesel, Euro 5 compliant at 50 ppm sulfur and Euro 6 compliant at 10 ppm sulfur is seen here. The accumulated soot on the DPF on the right renders it ineffective, which is why we emphasize that fuels and vehicles should be treated as the same system.
There's one caveat here to be aware of. Emission testing and type approval of engines and buses are often done in laboratory conditions, which do not represent the actual use case scenario of buses. Real-world performance emission measurements that are taken through portable emission measurement systems, PEMS, and remote sensing show a significant gap between standards and real-world performance for diesel vehicles. The gap depends on the duty cycles at which the vehicles operate, as well as emission standards to which the vehicles are subject to. The figure above shows how different heavy-duty vehicles from different eras have this phenomenon where real-world emissions far exceed laboratory results. Discrepancies were especially gaping in pre-Euro 6 emission standards.
While achieving unprecedented reduction in pollutants, they release to the atmosphere, Euro 6 or EPA 2010 soot-free diesel engines do not suffer fuel consumption penalties compared to engines that are only compatible with earlier emission standards. More variation within a single standard than there is across different standards, in fact. Manufacturers report even better fuel economy from their Euro 6 products and Euro 5 buses. Diesel engines are the main powertrain option for urban buses among operators, but the cleanest soot-free Euro 6 diesel buses are not quite mainstream. A recent UITP study of bus operators worldwide found that only less than 20% of operators today run fleets powered by Euro 6 technologies. The situation will likely change in the next few years as ultra-low sulfur diesel is made available in more markets around the world and emission standards are updated to Euro 6 equivalent levels. The ICCT projects that by 2025, under adopted and planned policies, 68% of new diesel buses would be equipped with DPFs, and new diesel buses purchases would be mostly Euro 6 diesel, as we are already witnessing in Mexico City's RTP fleet that recently introduced 106 Euro 6 diesel buses. In Dubai, UAE, Volvo buses and their local partners have been selected to supply 337 Euro 6 diesel buses to the Roads and Transport Authority. An alternative to conventional petroleum diesel is biodiesel, and biodiesel buses are being promoted in some areas of the world as a more environmentally friendly alternative. Biodiesel is made from vegetable oils and/or renewable animal fats. Biodiesel is often blended with petroleum diesel at a 5% to 20% ratio, especially in countries where biodiesel feedstock is readily available, like Indonesia. There's also renewable diesel, which, like biodiesel, is not from fossil fuels, but from biomass feedstocks. They come from non-petroleum renewable resources, such as natural fats, vegetable oils, and cooking oil waste that can be turned into renewable diesel. The chemical properties of renewable diesel are more similar to petroleum diesel than those of biodiesel. Biodiesel and renewable diesel can, in theory, achieve similar performance as petroleum diesel while delivering lower well-to-wheel life cycle CO2 emissions. However, the alleged reductions in GHG emissions should be scrutinized because of indirect land use change emissions to produce the feedstocks for these alternative types of diesel. This graph above is from our analysis of carbon emissions from different types of bus technologies for Sao Paulo's fleet. As it shows, biodiesel and renewable diesel have much lower tailpipe fossil CO2 and fuel life cycle CO2, not counting indirect land use change emissions. But once land use changes are included, the fuel life cycle CO2 might even exceed that of fossil diesel. To achieve low GHG emissions, lower carbon intensity fuels, such as those produced from animal fats or used cooking oils, should be prioritized. Now let's move on to talk about CNG buses. In the 1990s, there was an increased interest in the use of compressed natural gas buses around the globe. CNG buses had an advantage over diesel engines back then to address PM and NOx emissions for air pollution, and could also reduce reliance on oil imports. Unlike diesel engines that are compression ignition, natural gas engines are spark ignited and can use either a lean burn or stoichiometric combustion mixture. Emissions of conventional air pollutants such as NOx and PM depend on prevailing emission standards, Euro 4, 5, or 6, and modern CNG buses using stoichiometric combustion combined with exhaust gas recirculation and three-way catalyst aftertreatment systems can meet the most stringent Euro 6 emission standards. That said, CNG buses have higher levels of particulate number emissions than diesel buses. The oxidation catalyst for CNG buses oxidizes the organic fraction of the particulate matter, and this increases the particulate number size distribution emissions. With most state-of-the-art emission control technologies, Euro 6 CNG buses meet the definition of soot-free. Some operators choose to retrofit existing diesel buses to CNG to save costs. It's important to bear in mind that CNG buses need dedicated storage and refueling infrastructure. CNG buses' overall drivetrain efficiency is on par with diesel buses, But as this figure shows, CNG buses show greater variance in energy efficiency in the Altoona test. In terms of greenhouse gas emissions, CNG buses' tailpipe GHG emissions are 5% to 15% lower than diesel. In well-to-wheel terms, fossil-based CNG engines have GHG emissions on par with diesel, in part because of methane leakage issues. Methane, the main ingredient in natural gas, has 84 times more warming power than CO2 over a 20-year framework. Methane emissions and leakage may occur at the tailpipe, the engine crankcase, and from the fueling station. To save energy and reduce methane leakage, better management in the entire natural gas value chain is necessary. Depending on the market, CNG buses can be 10% or more expensive than Euro 6 diesel buses. The cost of gas refueling and storage infrastructure is an additional consideration when comparing them to diesel buses, for which the fuel is likely to be more available. Urban transit operators in cities across the world are purchasing Euro 6 CNG buses. Recent deployments include Los Angeles, Delhi, Jakarta, Lagos, as well as Stockholm and Ivory Coast. In Stockholm, the natural gas is not fossil but biogas. Like biodiesel and renewable diesel are for diesel fuel, there are also non-fossil sources of CNG, many of which are referred to as renewable natural gas. Organic matter such as waste and plants decompose to release biomethane from anaerobic digestion, which is then cleaned and conditioned to remove impurities and other non-methane compounds. Biomethane is likely to be more expensive than fossil-derived CNG unless policies are put in place to reduce price differential. This figure is adopted from California Resources Board's temporary pathways table for biomethane produced from landfill or digester gas. As we can see from this wide distribution of carbon intensity values, the type of feedstock determines whether biomethane can reduce greenhouse gas emissions from animal waste, which is most effective, to landfill gas, which almost have similar levels of carbon intensity as fossil fuel CNG. The last type of technology we'll talk about today is hybrid-powered buses. These buses are equipped with an internal combustion engine and an electric motor, generator, and batteries. There are generally two types of hybrids, series and parallel. A series drivetrain receives mechanical power from the electric motor, which is run by either a battery or an internal combustion engine-powered generator. In hybrids with parallel drivetrains, the electric motor and internal combustion engine can provide mechanical power simultaneously. The higher complexity of a hybrid bus implies a higher cost than conventional ICE buses. On the other hand, compared to fully electric battery electric buses, hybrid buses do not require an external electrical connection to charge the battery, and there are no infrastructure changes required when transitioning from diesel technology. Kinetic energy is recovered and used to recharge the battery onboard hybrid buses during braking events. Hybrid power may allow for engine downsizing and even partial electric-only operation, including engine shutoff when idle. Fuel consumption performance is highly dependent on route selection, ranging from 5% to 25% fuel consumption improvements. There's better performance in urban driving and stop-and-go traffic, which increases battery recharging events. Pollutant emissions would depend on the emission standard level of the engine, and hybrid buses would require the same quality of fuels as conventional combustion engine buses. In general, hybrid buses show lower NOx and PM emissions than conventional diesel buses. On slow and medium speed test cycles, hybrid buses have higher average fuel economy and operational savings than the diesel and CNG versions of the same bus. Higher speed test cycles, they generally have the same or lower average fuel economy and operational savings than the diesel version. As a result, total well-to-wheel GHG emissions are generally lower in hybrid buses than from diesel or CNG buses due to their higher fuel economy. This concludes Module 2A of our curriculum. Here are the messages we would like to take away. Euro 6 and EPA 2010 diesel buses reduce 90% of PM and NOx emissions and up to 99.5% of particulate number emissions without causing fuel economy penalties. Diesel buses' real-world emissions of NOx and PM are higher than during laboratory tests. Fossil fuel CNG buses have equivalent drivetrain efficiency, well-to-wheel GHG emissions, and PM and NOx emissions. With soot-free technologies, conventional pollutant emissions of the engine today are independent of the fuel type, but the fuel type does have an implication on well-to-wheel GHG emissions, depending on the type of feedstock used to produce the fuels. Hybrid buses save the most energy on low and medium-speed urban routes. Here are the publications referenced in the module and additional resources on the topic of internal combustion engine soot-free buses. Research and development of this curriculum is supported by Climate and Clean Air Coalition, International Climate Initiative, and Partnering for Green Growth and the Global Goals 2030. If you have any questions, please reach out to me at y.xie@theicct.org. Thank you.